Okay, I think we're a bit ahead of time, but nevertheless we may start. Next speaker is Paul Blackwell, and since we are back to animal movements.
Okay, thank you very much, and thank you to the organisers for the invitation. I'm going to talk about a little bit of very recent work in progress. That hasn't led to anomalous diffusion as I expected it to, but I hope it'll be of interest nevertheless. So I'm going to talk about animal movement with self-interaction, and starting with a paper by Bill Fagan and colleagues, who were recently looking at a model of animal movement using diffusion with self-interaction via some form of memory. And in that paper they discuss various possibilities, but they mainly focus on collection of models that have sort of dual memories, that have basically a homogeneous environment, and with a central attraction term. So when I say dual memories, they have essentially two terms affecting the movement. There's an attraction term, which comes from integrating over some function of past locations, and a repulsion term that is constructed in a similar way, but on a different timescale, potentially a different function of time. They have central attraction just to a single point in an environment that's otherwise uniform. So that's what I mean by there's no resources. There's no spatial heterogeneity except for this single point of attraction. So their model looks like this. So the movement of the location x is affected by this attraction term. So this is the integral of some function of elapsed time s times distance between the location at that time and the location at the current time, essentially times the direction between those 2 points. And a repulsion term, which is basically similar, but this time averaging function may be different. A linear attraction term towards this center mu, and then some noise term with a parameter delta. And they look at cases where those functions, the m's and the d, can be very general. They put some constraints on them to try and make biological sense. And they look at a variety of values for those key parameters, alpha, beta, gamma, and delta. And they refer to these as toy models. They're not intended to kind of exactly match a given biological situation. But nevertheless, they're quite complex models because at any given time instant, in order to figure out these terms, you need to evaluate this derivative. So they explore these models at some length by simulation. And they talk about the fact that they're limited in how much they can explore purely by the computational cost of implementing these. And they talk about three sort of qualitatively different kinds of behavior that they observe in these models, which they refer to as attractive points, essentially where some combination of alpha and gamma is large enough that the trajectories essentially collapse to a point, but with some sort of persistent noise due to the delta term. Cycles where the trajectories settle down to some loop around the point of attraction mu, and what they call distributions, which are essentially sort of noisier versions where there's no cyclic behavior. It's clearly a center, but there's a lot of variation around that. And so these are, with permission, these are pictures from the Fagan et al. Paper. So this is what they mean by an attractive point. The trajectories start off very noisy, but over time they collapse essentially to a point. The most interesting kind of behavior is these cycles. so the behavior settles down to a cycle. In some cases, it retains these sort of sub-loops, but eventually those tend to disappear. This is another example with slightly different parameter values where convergence to that cycle is much quicker and it simplifies much more quickly. And then these are the sort of things that they refer to as distributions. So they're essentially just very noisy sets of trajectories around a center. So I wanted to sort of take that toy model, as they call it, and simplify it further and think about, is it possible to explain some of what's going on more analytically? Can we simplify the computation, make the toy easier to play with? And some more specific questions. So, I mean, the formation of those cycles is particularly of interest as a phenomenon and biologically. But yet, in their environment, I mean, apart from the memory terms, they have a very simple environment. They just have a point of attraction mu. And in the absence of the memory terms, you would expect the animal to spend most time closest to mu. But that doesn't happen in those cycles, obviously. And sort of connected with that, do we actually need that attraction term? I mean, Fagan et al. Sort of think that probably do to see the kind of behavior that they get, but it's not. I think it's immediately obvious that's the case. So I wanted to explore some of those things. So they mainly, I mean, they look at various choices, but they mainly take those M functions, the functions of memory with respect to time, as being exponentially decaying. And I'll do I will do the same thing. I'll parameterize it slightly differently. It turns out to be convenient to write them as densities. So these look, I mean, there's nothing probabilistic going on, but they're written as if they were exponential densities. And like them, I'll always take kappa to be larger than lambda, so that the attraction is over a longer term than repulsion. But I'll greatly simplify their models by taking that function d, the function of distance that comes into that integral, to be the identity. We go some way to sort of undoing that later on. And that's purely for tractability. So if we do that, then we have a much simpler model. We just have an attraction term that's the integral of this exponentially decaying density times this difference between the old location and the current location. Similarly for the repulsion term. And actually, it's convenient if we think of those integrals as going all the way back to infinity, because then, having written this as density, this integral of the xt term just becomes xt itself. And if we do that, then we can write the whole model for x like this. We just have alpha times the difference between some memory term, mt, and the current location. Similarly, repulsion times, we have a sort of secondary, or second memory, nt. And each of these is the integral, right back to infinity, of an x. It's an exponentially decaying average of all past locations. And of course, depending on how we want to sort of set things up, back beyond time 0, so for s bigger than t, this thing isn't necessarily well defined, but we can think of the sort of tail of that integral as just representing an initial setting for the memory, just an initial condition. So we've now gone from having a model where we had to think about those integrals in a fairly sort of abstract sense, to now being able to think about them in terms of some locations, M and N, that are varying with time, and the attraction and repulsion is related purely to those. So in this picture, so the red dot is the initial location of the animal, and the red trace here is its trajectory. The green term here represents so M of t, so the memory that's expressed as a point, which is then exerting an attraction on the animal. And similarly, the blue curve is, again, the N of t, so it's a memory that's changing over time and exerting a repulsion on the animal. And although I won't sort of focus on it, the dotted unit circle here, that's there as a kind of reminder that we have to set up those initial memories somehow, and for reasons that will become clear, typically I'll do those by pretending that before time 0, the animal was following a trajectory defined by the unit circle. It's not crucial, but it's typically what I've done. So we now have this much simpler form for x, and also because we're taking the exponential decay for mt and nt, we can write down the equations for the updating of those in a very simple way. We have this very simple linear system. So xt is related linearly to m and n, and m and n are related linearly to x. So we've now reduced the system. Instead of having to keep track of location back over the whole of time, the values of x and m and n now completely define the system. So we've gone from a non-Markovian system to a very simple Markovian system by sort of simplifying the memories in that way. And it's a Markovian system that has a kind of spatial intuition to it, because you can think of those memories as being points in space. And also, in this sort of linear version, we can separate out the coordinates. We can analyze the x coordinate, the y coordinate separately, and they're both described by this very simple linear system. And the kind of the essence of it is captured in this matrix here. And so, there's different ways you can sort of think about the set of equations. One way of doing it is that we now have for each coordinate we have this three-dimensional system, which is just an Ornstein-Uhlenbeck process, and its dynamics are controlled by this matrix A. So what I want to do is use that to look at the sort of the dynamics of this simplified version, the kind of kindergarten version of their toy model, and see what we can learn analytically about that. And the natural thing to do is to look at that matrix A and look at its eigenvalues. And in particular, as I said at the beginning, I wanted to kind of query this gamma term, this central attraction, which is the only inhomogeneity in the space in their model. So if gamma is 0, then it's very easy to write down the eigenvalues of A analytically. In fact, if gamma is 0, so if there's no heterogeneity at all and no fixed central attraction term, there's always an eigenvalue of 0, and the remaining eigenvalues are of this form. So just looking at this quantity rho, which is just has a very simple relationship with those parameters, tells us most of what we might want to know about the dynamics. So in particular, when rho is 0, the real parts of all of these eigenvalues are 0. So then, if we think sort of temporarily about the case without noise, so if we set delta to 0, what we get as sort of equilibrium paths in that model is we just get cycles, either circles or actually any ellipse forms a sort of equilibrium path. So we get that cyclic pattern even though there's no central attraction, it just arises through the memory terms. And the particular ellipse that we get, not just its shape, but also its center, purely depend on the initial values. Because if we set gamma to 0, then the space is completely homogeneous. We don't have, mu doesn't come into the model anymore. So these paths, these elliptical paths, are equilibrium paths, regardless of which ellipse we choose. If we add the noise back in, all of that remains true, but now the particular ellipse that the system is following changes gradually over time. So the paths aren't actually stable, but the system, there's essentially two sort of timescales, may or may not be very well separated. The paths follow this ellipse, but also the parameters of that ellipse change over time. So this is just an example of that. And as with a lot of these plots, I've kind of turned down the noise a lot to make it a bit easier to see what's going on. So we start off here, again, initialized as if it was going around the unit circle, which in this case would be a possible equilibrium path, but it moves off that path fairly quickly, and you can see that the sort of same kind of tendency continues, but by the end it's kind of moved to more of an ellipse, and the center has drifted downwards a bit. So that's the case when rho is 0. If rho is less than 0, then the matrix A is nearly stable. It still has one eigenvalue of 0. The others have a negative real part. So again, we have these sort of this separation of timescales. The process is attracted to some center, but it's not a fixed center unless there's no noise, unless delta equals 0. If delta's strictly positive, then that center itself is diffusing around, just diffusing very slowly compared with the sort of movement of the scale of the noise of the movement of the individual animal. And in a sense, broadly speaking, if we look back to the behaviors that Fagan et al. Observed, whether this case amounts to what they call a point or a distribution purely depends on delta. It doesn't depend on the dynamic parameters, just on the noise parameter. If delta is small, then essentially everything collapses to a point with a little bit of noise around that, and that point is itself diffusing slowly. If delta is bigger, then there's a lot more variation around that point, but essentially the same thing's happening. If that quantity rho is positive, then the matrix A is unstable. There are eigenvalues with positive real part, and the whole system will sort of the whole system is unstable. And it's perhaps worth pointing out that in that situation, when rho is bigger than 0, you get this sort of extreme movement away from past locations, and that's a case where the sort of extra simplification that I've done in making things linear is particularly unrealistic. Broadly speaking, the different kinds of behavior that Fagan et al. Saw can all occur with gamma equals 0. They're not identical because, of course, when gamma equals 0, there is no fixed center, but we still get patterns that, basically speaking, look like what they observed, despite not having that fixed central attraction to it. And so just sort of examples of that. So this is a case where rho is negative. Again, I've initialized it sort of as if it was going to go around the unit circle, but of course the parameters are, don't fit with that, and it very quickly collapses to a relatively small region. You can see the sort of tendency to continue. There's still a sort of circular element to it, but it collapses down to a relatively small area. And if you do the same thing, but with a bigger value of delta, so just a noisier case, everything else is the same, then as you'd expect, you get something closer to what they refer to as a distribution. You get something that's sort of more spread around some center. There's kind of arbitrariness in where the center ends up being. So broadly speaking, all the kinds of qualitative behavior that they observed, plus sort of divergence that you get when rho is greater than 0, can all be reproduced within this version, with gamma being 0. It's still of some interest to look at what happens when you do have the gamma term. So I just want to think briefly about sort of adding that back in. So if we do that, now there really is a center. This is a sort of proper OU process. There's a center. We can look at each coordinate separately. So the x coordinate has a center at mu x, the y at mu y. What happens when we vary gamma? If gamma's large, so in addition to the memory terms, we've got a strong attraction to this center at mu, then unsurprisingly, A really is stable, and so you get a process that simply sort of spends its time around that true center mu. How dispersed it is over time around that center depends completely on delta, and it's possible in principle to calculate that. So again, we get sort of either the point or distribution forms. It seems, well, certainly with this kindergarten version, you don't get cycles when gamma's not 0. So in this linearized version of their model, with gamma being non-zero, you no longer get cycles. But something interesting does happen if you think about gamma being small, so a small central attraction. So if gamma is large, then you always get stable matrix. You always get a sort of collapse to a point. But for small gamma, it depends on the other parameters. So if you, in principle, you can look at the eigenvalues algebraically, even if gamma's non-zero, but the expressions are really horrible. So it's easier to look at it numerically. So if we look at what happens numerically to the real parts of the eigenvalues as we vary gamma, this is what happens, or at least what can happen. So if we start off in a case where we have values for the other parameters such that if gamma was 0, then we'd have 0 parts to all the eigenvalues. That's to say, we're in the case where without gamma, cycles would occur. That cyclic type behavior. And then we look at varying gamma. If you increase gamma just a little, what happens is that actually the real part of the complex eigenvalues becomes positive for small gamma. and then becomes negative for larger gamma. So what that means is that in this model, if you start with a situation where there is cyclic behavior and add in an attraction term to a center, I can actually turn that behavior into not stable but unstable sort of divergent behavior. And just a quick example of that. Yeah. So this is a case, this is with gamma equals 0. Again, the noise is turned down fairly low. Started off as if it had been going around the unit circle, and because I've chosen parameters so that rho is 0, it sort of pretty much continues to do that, but there's a bit of drift in the particular ellipse that it's following. You have this cyclic behavior. So that's with gamma equals 0. If we then add in a small attraction term to the center, we get very rapid divergence. I mean, you're still getting trajectories that in the short term look elliptical, but they're very clearly divergent. And then if you sort of continue to increase gamma, then you do quite quickly switch to a stable regime. And again, you're still getting, with this particular choice of parameters, you're still getting a strong sort of cyclic component, but it's spiraling in towards some center. So the effect of gamma, on the one hand, you don't need gamma to get the range of qualitative behavior that they observe, but if you do have gamma, then its effect is not always intuitive. So I just want to talk briefly about taking that very simplified model and adding back in some of the sort of a little bit more scope for realism. So I want to sort of retain some of the simplicity by thinking about these points that represent the memory, M and N. So I still want to keep the sort of exponential decay with time in constructing the memory, but I want to think about allowing the attraction and repulsion terms to depend more generally on distance. Okay, so I want to just think a little bit about this version where the attraction term, for example, is now the parameter alpha times some function of the distance between the sort of average remembered location M and the current location X, times that actual vector difference. So this is just a scalar function that will scale the magnitude of that attraction. This is not putting back in that nonlinearity in the way that Fagan et al. Had it, but it does allow for a kind of slightly more realistic, particularly in the sort of repulsion at large separation case, adds in a bit more realism. So certainly we can't separate out the coordinates anymore. Can't treat X and Y completely separately. But actually some questions about this system we can still sort of investigate based on that previous analysis. So in particular, the sort of transitional behavior between the sort of stable and the unstable behavior, when we've got the cycles, we can still use that previous eigenanalysis to figure out when a cycle of a given radius is going to be an equilibrium trajectory. Now, because of the nonlinearity, which radius we have does matter, whereas before it was just something that didn't enter into the figuring out those equilibrium paths. Now it does, but we can say we can use the previous analysis to say when is there a stable cycle or an equilibrium cycle of a particular radius. Because if that's true, then of course the distances between x and m and n aren't changing. They're all kind of cycling together. And so we can use the values of the attraction and repulsion at those appropriate distances and sort of piggyback on the eigenanalysis. Of course, the details of behavior depend very much on the shape of those functions g and h. And I'm not going to try and go into those exhaustively, but in many ways, for sort of what seem like sensible choices, we get behavior that's more similar in some ways, even if we don't have the attraction term, even if gamma's 0, it's purely memory, we get behavior that's closer to what Fagan et al. Saw, in the sense that those equilibrium cycles are now stable, I mean, still stable in quotes, stable in the sense that there's a tendency, given a parameter set, there's a tendency to cycle with a particular radius. It's not really stable because the center of that equilibrium path is still going to diffuse. So we have still have these two different timescales, but now on the sort of shorter timescale, the radius of those cycles is set by the parameters. So this is just a quick example of that. And I've turned the noise off completely here. And so with these particular conditions, I've set it up I've initialized it as if everything was still linear and it had been going around the unit circle. But the parameters are such that I'll put in a sort of decaying function for the repulsion term, which is a much more sensible thing to do from a biological perspective, such that the sort of equilibrium radius is now half rather than 1, and you get this convergence to a cyclic path of that sort of radius, but the center of that is not at the origin, which was the center that had been used in initializing the memories. It's some function that you can write down of the initial conditions. So it converges to some other set of cycles. If you add a bit of noise in, then basically the same kind of thing happens, but more slowly. Again, so it's still only a tiny amount of noise. Realistically, you'd want much higher noise than that. So you can get essentially stable paths in the short term, still have this longer term diffusing of the center, and that seems to be a fairly robust property of having non-linear decay with distance of the repulsion term. Alternatively, another way of adding back some realism into the kindergarten model is to think about how memory varies over time. So putting in exponential decay in the way that I've done is really convenient because that's what takes us from having sort of non-Markov process where we have to keep track of the whole location history down to a very simple Markov process where we only have to keep track of m and n. But that exponential decay inherently means that it's the most recent locations that are most important. The timescale of that is different between the attraction and repulsion terms, but the shape of that exponential decay means that the most recent locations dominate, and the shape of that is fixed. And maybe for the repulsion term, that's not too unreasonable. We're trying to capture in repulsion some idea that the animal doesn't want to be where it's been recently. Whether that's just kind of proxy for some sort of velocity effect, or whether it's avoidance of local depletion, whatever. The model, we're not trying to be specific about that, but it's sort of plausible that repulsion term might depend on what's happened most recently. Depending on what we're trying to express, it's not at all clear that that applies to the attraction term. There's all sorts of plausible reasons why you might want to think about the dependence in the attraction term on elapsed time should be different. Fagan et al. Mainly use functions where there's a sort of fairly slow decay in the short term, and then it tails off quite rapidly. So that the animal sort of has a memory of where it's been fairly recently, but then much less memory beyond that. On the other hand, there are certainly arguments for that function not even being monotonic, that the most recent place for attraction might not be the most important. So, for example, in real behavior, you often see a phenomenon known as trap lining, which corresponds to the kind of cycles that we've been getting here, where the animal is sort of revisiting past locations where it successfully found prey or whatever in a cyclic way. And so actually, you might want to think about the attraction being more focused on what happened at a particular time in the past. So, turns out we can do that, at least to some extent, without losing the kind of advantages of this nice finite dimensional Markov representation that I've got. So, basically, you can think about replacing each part of the memory, so each of m and n for each of the coordinates, which currently is a scalar. So at the moment we have we have an mx and an my, and an nx and an ny. We can replace some of those with vectors. Keep the sort of the structure whereby the different components interact in a linear way, but now have multiple components of memory. And you can sort of draw an analogy between the memory of a particular location decaying over time with a particle passing through a continuous time sort of finite state Markov chain. So in the case that we've been looking at so far, essentially you just have a sort of time where that particle is in a particular state, and at some point it leaves that, and obviously that has an exponential time. But if we now think about Markov chain with multiple states and look at the exit time from that group of states, that has a much more general, as a phase type distribution. And that kind of carries over to this structure. If we think about having multiple components to one of these memories and tracking how a location's weight decays over time, then in exactly the same way we can set things up so that decay function looks like the density of a phase type distribution. Okay, so a very simple example of that. If we just think about the attraction term, and instead of that being exponential, if we think about having two components to that, both decaying with the same rate lambda, but it's only the first term that directly influences x. The second term is there simply to influence the first term in the memory. So the memory of any given location kind of passes through influencing the second component, and then passes through influencing the first component. If we do that, then the distribution of weight attached to a particular memory over time, that looks like an Erlang 2 distribution. So it's a very simple example, but it's enough to give us a peak at a place that isn't the origin. And this is an example doing that. The Erlang 2 actually isn't enough to get any terribly interesting behavior out, but just to sort of illustrate the idea, we have the red curve as before, which is the actual location. The blue curve as before is the component memory that represents repulsion, and now we have two attractive components. The solid green line is what's attracting the actual location of the animal, and the dashed green line is what's doing the averaging of current location and influencing the solid green line. So we have, this is at M1 and this is at M2. But any positive distribution can be approximated by a phase type distribution. So if we're willing to have a bigger vector to represent memory, we can very easily generate any kind of decay function over time in that way. So for example, we could arrange things so that there was a peak in the attraction term at the time representing a day or a year, depending what kind of phenomena we're trying to capture. We still have a nice finite Markov representation and some sort of spatial intuition about what's going on. Okay, so just to sum up, so this approach hopefully gives a bit of extra intuition to what's going on in how memory is influencing movement, and at least some analytical insight in some cases. It's easier to play with because computationally it's very, very fast. The different kinds of qualitative behavior, broadly speaking at least, that Fagan et al. Saw all occur within this model, even without the attraction term gamma. And if we do have gamma, then at least in some cases, its effect is not intuitive. There's a lot more to explore, particularly in the case where the distance function is not linear. I think there's a lot to say about that. And also, it'd be really interesting to explore if you try and build in some real heterogeneity, as opposed to simply a central point of attraction, what kind of behaviors you get in that case. Okay, and I'll stop there. Thank you.
Thank you very much. Questions? So it seems the biological motivation was really to understand phenomena like trap lining.
In part, I mean, it depends which end you start. It's to think about what kinds of things might be influenced by simple representation of memory, or, I mean, and given the sorts of things that occur, yeah, then questions about things like trap lining. I mean, I think
mathematically this is kind of self-control, right? So that belongs to a problem of what's generally called control theory, I suppose. In dynamic systems, for example, you plug in control terms, but typically then it's not self-control, but rather you want to force a dynamic, say, onto a certain fixed point or something like that. Which indeed now, if this was trap lining, probably you would have to put in some spatial control as well, right?
I mean, it depends how kind of precisely you want to try and capture that. I mean, obviously, real trap lining, in part, is a response to the sort of detailed local heterogeneity. But I guess the way I would think about it is that in environments or for species where that sort of behavior would make sense, then you would expect to see parameter values that lead to the kind of cyclic behavior that we've seen in the sort of very simplified case. But yeah, the details are always going to be sort of environment dependent.
Okay. Anything else?
If the memory is indeed in diffusion, noise part, Does it change?
Yeah, yeah. I mean, well, there's actually, if the memory affects the diffusion, then yeah, that immediately is going to. I mean, it'll be really interesting, but it's immediately much more complicated. I mean, the other thing that's sort of simpler to think about would be if the diffusion affects the memory, i.e., if the memory is less precise, because at the moment, just for simplicity, the noise only comes into the location term. Now, I mean, that wouldn't affect the linear part, so that matrix A would be unchanged, so some aspects would clearly stay the same, but you would see some change in the behavior, clearly. But yeah, I mean, building memory into the diffusion itself would certainly be interesting, but I haven't explored that at all.
Okay.
One question.
Yeah.
It's more thinking out loud, but if you were to say, well, you know, memory is going to affect decision when something extreme happened, can you model it by saying, you know, the repulsion got above a certain threshold, and this is what I remember, or you know,
So then you're talking about a sort of a more complex way of deciding what to remember. I mean, obviously within the sort of original Fagan et al. Model, you can do things like that because you have a lot of flexibility in how you calculate the memory, but you're recalculating it all the time. With a kind of, if you want to retain those sort of finite Markov representation, there are definitely some things that you can do in the same way that I was talking about at the end with the sort of having a sort of vector form of the memory, or maybe, I mean, maybe the thing is not to remember the sort of average location, but to remember some spatially averaged function of what happened there. And I think that would be kind of plausible, and might be at least to some extent tractable, but I haven't explored that. But it would certainly be interesting. Thank you.
Okay, we need to move on, so thank you very much again.